So what we're covering today is more solving systems, but now our system is in a three-dimensional plane. So that third dimension, just to kind of provide context, when we're in two dimensions, we say that something kind of has length and width, right? So kind of like the paper in front of you, right? We can measure how wide it is. We can measure how long it is from bottom to top. That'd be a two-dimension. When we add the third dimension in, now we're adding depth. So a really good example of like a three-dimensional figure in this room is this pillar, right? The two pillars in the middle of the room here. We can measure how wide it is, we can measure how tall it is, and we can measure how deep it goes. Okay, so adding that third dimension, there's another variable involved with it. That new variable is the z-axis. So in three dimensions, you still have an x-axis and a y-axis, and that depth axis is now z. So when we're stating a solution to a solution or to a system with three variables, it's x, y, and z. That third variable adds a lot more work to us. So here's kind of what visually happens when we have three dimensions. So we saw this with one of the SAT questions that you all did last block period, that when we have a system, the solution to that system is where all the lines or all the parts or all the equations intersect. So what is the one place that they all intersect at? These no solutions, while we're seeing a lot of these planes, so planes are in two dimensions. So if we've got planes that intersect, that's fine. But all of these are not showing where these planes might intersect in one common place. So yes, there's points of intersection, but not one single point where they all intersect. What we're looking for, and when we'll have solutions, is when we have these planes intersect at one given point where they all intersect. So a good example of that is like a corner. Okay, on the pillar here, the corner is an intersection of the length, width, and depth, okay, where they all meet together. It is also possible for us to have infinite number of solutions where all the planes are intersecting on a line. Okay, that's a kind of a unique case here. And again, you don't do a lot with three-dimensional space until you get deep into calculus. And when I say deep, I mean like Calc 3. So for me with a math major, I didn't take Calc 3 until like my junior year. So a lot of you probably won't even do stuff with three-dimensional space with math in your math careers, okay? But the solving is what we're going to focus on, okay? The solving, again, can be a little bit tedious. It gets us more thinking about elimination and substitution again. So, again, we can use either method. I'm going to just strictly use elimination. I think that's much easier. I don't really like those words. Let's just jump into the examples. Okay, so to me, it is most help. The more organized your work is, the better off you're going to be. Now, another thing that I'm going to do when I go through examples is number my equations. So I have equations 1, 2, and 3. And go ahead and write those down and give you a second to do so. Okay, so the first thing that we want to do is eliminate one of these third variables. And we want to create a system that has two variables, which we're familiar with solving those. So the first task is, can we create two equations that just have either x and y, x and z, y and z, it doesn't matter. But we want two equations with two variables. So what I'm looking for is there a way that I can add two of these equations and eliminate one variable off the bat? And I'm noticing that if I add 1 and 2 together, the z's go away. So we're going to start with that right off the bat. So 1 and 2. So 2x minus y plus z, and x plus 3y minus z equals 11. So the whole point of us adding those together was to eliminate a variable. In this case, we're eliminating z. Then I'm adding them together, just like when we do elimination with two variables. So this gives me 3x Negative y plus 3y is 2y, and it equals 15. So we've created a whole new equation. Let's give this equation a number as well, because we're going to use it again. Let's call this equation 4. And we need a second equation that has these same variables. So we need to create a fifth equation that has just x's and just y's. And again, I'm noticing that if I add 1 and 3 now, so a different combination of the original equations, that'll give me a new equation that can be our equation 5, where the z has been eliminated. So we're going to do 1 and 3. So 2x minus y plus z equals 4. And then 4x plus y minus z equals 14. So adding these together, 2x and 4x is 6x. The y's eliminate. That was kind of unintentional and not what my main purpose was. My main purpose of adding 1 and 3 was to ultimately eliminate the z's, but it just so happened that the y's also eliminated. That actually makes this a little bit easier. And so we have that 6x equals 18. Now, why this is easier is because we can find the value of x right away, right? I know that x, if I divide both sides by 6, is equal to 3. Once we have a value of x, I can plug that back in to find another missing variable, and we want to plug it in to the equation that just has x and y. That's going to allow me to find the exact value of y, and if we know x and then y, then we can find z by plugging those numbers back in. So now I'm going to take x equals 3 and plug it into 4. So this is 3 times 3 plus 2y equals 15. So 9 plus 2y equals 15. So 2y equals 6. And thus y is also 3. And now that we have x and y, to find z, we just need to take these values and plug it back into any of the original equations that we started with. Okay, because now knowing x and y, we can replace those variables, and the only missing variable now will be z. So let's just plug it into 1. Again, it doesn't matter. So 2 times 3 minus y, which is 3, plus z equals 4. So this is 6 minus 3 plus z equals 4. So 3 plus z equals 4, and thus z equals 1. So our solution, again, is the point where these all represents planes. Okay, they're not lines anymore. When we have that third variable, now it's a plane. So all three of these planes intersect at the one common point of 3, 3, 1. So it's like its length is 3, its width is 3, and its depth is 1. Okay, so we got a little lucky with that one because of the y's and the z's eliminating. It's not going to always work out that nicely, but when it does, the work goes a little bit quicker. Okay, when it doesn't, we had a little more work to do. Yeah. All right, so once you're done with that problem, go ahead and write down the next one. I'm going to just pop. Okay. So just like before, let's number these equations just so that it's easy to kind of reference back to. So we got equation 1, 2, and 3. And again, the first task is to add two equations together and eliminate one variable. If that happens already, meaning if we already notice we can do that, we'll just add them together. But just like before with elimination, you might need to multiply one or even both equations in order to eliminate one of those variables. I'm noticing that if I add 1 and 2, I'm going to get the y's to eliminate. So we don't need to multiply yet. So let's just do that right off the bat. Equation 1 and equation 2. X minus y plus z equals -1. Then x plus y plus 3z equals -3. Again, the whole point of us adding these two equations together is for the y's to eliminate. And that gives us 2x plus 4z equals -4. So now we basically need to repeat that exact same step. Okay, creating an equation that just has x and z, but it needs to be a new equation. So we got to add a different combination of equations together. So I'm also noticing that if I add 2 and 3 together, again, the y's will eliminate. And that's what we need to focus on, is eliminating the y's one more time. So let's do 2 and 3. So x plus y plus 3z equals -3. And 2x minus y plus 2z equals 0. So x and 2x, that's 3x. The y's eliminate. That's the main thing we were trying to accomplish here. And then 3z and 2z is 5z. And it equals -3. Again, we can give these equations names or numbers. So that's 4, that's 5. And what we've just accomplished is we've created a system with 2 variables and 2 equations. Exactly what we had just quizzed on in 3.1 and 3.3. So we can now use these 2 equations to solve for x or z, and you can use elimination, you can use substitution, whatever you're more comfortable with. I almost always stick to elimination. That makes sure, it guarantees that we don't have to work with fractions unless our answer is a fraction. But what I'm going to do is I'm going to take equations 4 and 5, and I'm going to use elimination to solve for one of those variables, either x or z. And right now, if I add them together, I'm not going to get any variable to eliminate. So this is the case where I'm probably going to have to multiply both equations. And it doesn't matter which one we eliminate. I always go with the one that has the smaller coefficients, so that would be the x's here. So I'm going to multiply the top equation by -3. That's going to give me a -6x, and the bottom equation by 2. Remember that when we multiply, every single part needs to get multiplied, and a lot of you are forgetting to multiply the constant value. And so that gives us -6x minus 12z equals 12, and then 6x plus 10z equals -9. So adding these together, the x's eliminate. -12z plus 10z is -2z, and it equals, how about -6? Check your multiplication, Mr. Youngren. Which is much better because now we don't get a fraction. Nervous there for a second. Not that we can't work with a fraction, it's just a little bit messier. But divided by -2, we get that z is -3. Once we have the value of z, now our task is to plug this into one of the equations that allows us to solve for another variable. So that's our equation 4 or 5. If I plug z into 4 or 5, that's going to allow us to solve for x. And then once we know x and z, that's when we'll go back to the 3 originals. So let's use equation 4. So 2x plus 4z, which is -3, equals -4. So 2x minus 12 equals -4. And then adding 12, I get that 2x equals 8, and x is 4. And now that I know x and z, I can take these two values, plug it into either equation 1, 2, or 3, which will help us find y. So I'm going to go equation 1. So 4 minus y. We don't know y yet. That's what we're looking for. Plus negative 3 equals negative 1. So 4 minus 3 is 1. So negative y plus 1 equals negative 1. Then minus 1. So negative y equals negative 2. And thus y is 2. And again, our solution, the point where all three of these planes intersect, is 4, 2, and negative 3. X, Y, Z. Okay, so you can see what I mean by it being tedious, right? And the more organized your work is, the easier it's going to be, especially if you kind of get lost in your work or if you're in the middle of a problem and have to stop. Numbering the equations is another useful thing, but it's just a ton of elimination, right? Just eliminating all over the place. And your first task will always get to a system with 2 variables. So as of now, all right, for everyone online, I'm going to have you work through this problem before we're going to go back and do one more. But go ahead and work through this system. And just so that your work matches mine, I'm going to have you eliminate z by first using equations 1 and 3, then again with equations 1 and 2. Go ahead and do that, work through the entire problem, see if you can't come up with a solution of x, y, z, and then we'll check our work once you unpause the video. This worked out a lot like the first one that we did, and especially, I wasn't even really paying attention to it, but when we add equations 1 and 3 together, and what's nice about that is it gives us a value of x right off the bat. Now, even when we get that first initial value, in order for us to then find the value of y or z, we need to create an equation that has x and then either y or z. So still adding 1 and 2 is something that we need to do. And so when I add equations 1 and 2, the z's won't eliminate right off the bat, but I'm noticing that if I multiply the top equation by 2, that gives me that 2z, which will then eliminate. So I multiplied the top equation by 2. That gave me a new equation for equation 1. And again, the whole point of that was so that the x's will eliminate. So then negative 4x plus 2x is negative 2x. Y minus 4y is negative 3y. And 1 minus 8 is negative 7. So now that I have this equation with x and another variable, I can take the value of x, plug it in, and help me solve for y. And so what ends up happening is I get y to equal a positive 1. And once you have 2 variables, to find the third, again, you just take the 2 known variables and plug it into any original equation where I get z to equal negative 4. And so your solution here, x, y, z, is 2, 1, negative 4. All right. We're going to do one last equation together, one last system. And it just looks a little bit different. And one thing I'll point out before we move on, I know some of you are still writing this down too. It's really important with these, especially like when we get to the point where some of our problems are getting longer, right? The linear programming problems take time. Systems with 3 variables take time. They're tedious. With these, go slow and check your work, right? Because you can do everything right. But if you mess up like one sign, calling one thing negative when it should be positive, everything else from there is going to be off. Now, when I grade this, like when you're taking tests, I look for that. So I'm still looking, if you get a wrong value initially, does everything else from there match up with what you should do? Okay, with every test, I'm always looking to give you all partial credit. But a lot of times, if you mess that up, that might entail that you're going to work with some nastier numbers. So be careful, go slow, keep your work organized. All those things help make these problems not feel so lengthy and tedious. Okay, one last one, and then you're going to get not a ton of time today, but again, Friday will be a complete work day for you all. It says, what is the x value in the solution? We're just going to straight up solve the solution. And go ahead and jot down those equations to start. Right now, I'm noticing we just have one equation with x, y, and z. The other two equations have x and 5y, or x and y, and then z and x. And so I think if I just ask you all to try to figure this out from here, we'd be like, well, we're not quite sure where to even begin. And again, we want to think about what we're trying to accomplish initially. We're trying to accomplish getting two equations that have the same two variables. Right now, we don't have that, right? 2 and 3, they have two variables, but they're not the exact same. One has x, one has y, one has x and z. So what I'm thinking is I want to create a second equation that either has x and y or z and x. So we need to use equation 1, and then let's pick one of the equations we want to match it up with. Let's go with equation 2. So I want to work to get a second equation that has x's and z's. So that means I'm going to take equation 1, 2x plus 3y minus 2z, which equals -1. And then we're going to use equation 3 to eliminate the z's and give us an equation with x's and y's. But you'll look at this and you're like, wait, there aren't any y's in the equation. Well, we can add in y's without changing the value of it if it's a 0y. So we're going to actually do two things here. I'm going to rearrange this equation just so that my x's are stacked on top of x's, y's on top of y's, and z's on top of z's. So this is -5x. There's no y's, so I'll come back to that in a second. And the 4z is positive, so plus 4z, and it equals 4. So we almost just want to add in a placeholder for the y's without changing the equation. The only way that we can add something to an equation without changing it is to add 0. So this is a 0y. Now, do you need to write that? No. But again, it's helpful for now when I go to add my equations together. I've got two terms with y's that I can add and come up with a value or a coefficient for the y. So again, I'm trying to get x's and y's, so we're going to eliminate z. And I can do that by multiplying the top equation by 2. I do not know why this camera will not focus. So that gives me 4x plus 6y minus 4z equals -2. So the z's eliminate. 4z minus 4z go away. The x's, -5x plus 4x is -x. And then 0y plus 6y is 6y. And it equals 2. We'll call this equation 4. And now, which has x's and y's, and I can work to eliminate one of the variables, either x's or y's. And I'm noticing that x's will eliminate right from the start just by adding them together. So x minus x go away. 6y and 5y is 11y, and it equals 11, and thus y equals 1. Then to find any other variable, I'm going to take this value of y, plug it into one of my equations that has y and either just x or just z. That would either be equation 2 or 4. Let's just go with 2. So using equation 2, I have that x plus 5 times 1 equals 9, or x plus 5 equals 9, which means x is 4. Now that we have x and y, we could actually use equation 3 to find z and not have to plug both of them in. I'm going to do that. So I'm going to go 4z minus 5 times 4, and that equals 4. So 4z minus 20 equals 4. 4z equals 24, and thus z equals 6. And so our solution is 4, 1, 6. All right, so ended up not being too bad, but again, just that kind of starting point felt a little bit different than what we had done previously.